Okay. The homework assignment that is related to the rational method, that's due on Thursday. And I think as I was walking in, I heard some of you talking about the parking lot and putting the die in to try and figure out where the brake line is for how much of that parking lot contributes in a certain direction. It definitely does help to go out there on a rainy day. It looks pretty cloudy. We may get rain today. So that would be opportune. But if not, I mean, it just is an estimate. I just want you to start thinking in terms of how does the water move over a surface. And that's the point of that problem on the assignment. So that's due on Thursday, and as per usual, the procedure there is just to scan it to a PDF, upload the PDF to MU Online before class. So you'll have till 9:30 on Thursday. Also on Thursday, we're going to have a quiz. And so what I would encourage you to do for the quiz is be well acquainted with the material that was presented in those videos. So part of the quiz is just to follow up and encourage you to actually review the videos and not just take a week off from classes when I'm taking a week off from classes. Do as I say, not as I do, you know. But it's also going to be the first chance to see if the vocabulary and terminology list is working for you. So there are the terms on there that I'd like you to be able to answer some short answer questions on the quiz. So we'll do that at the beginning of class. Now the next assignment, which I'm going to actually give you a paper copy of today, because it's such a special assignment, that's due on Tuesday, September 12th. So you'll have a week from today to complete that. I think it'll take you far less time than some of the other assignments through the semester, just because it's using a software package that's pretty efficient, and you guys already are acquainted with how to use the Bentley hydrology software, and a lot of the functionality is the same. So I think it'll be pretty simple for you to knock this homework 3 out. So we're going to be talking about StormCAD today, and then on Thursday we're going to be talking about stormwater detention, which is the second half of this assignment. And since I've already mentioned it, let me just hand out the paper copies. I'll also upload the PDF onto MU Online as I usually do. But I wanted to give you this paper copy just so that as we're working through some examples today, you could look at how they might relate to what you're going to be expected to know and do for the homework. All right. But before we get into StormCAD, let's just review very briefly the rational method. And I want to do this example to drive home the point of what are the units of the rational method, the units of flow rate when you multiply everything together, because there's just kind of an interesting coincidence when it comes to the traditional units for Q equals CIA. So I'm going to pause for just a moment and allow you to calculate both in the traditional units and also in SI, what's the peak runoff for a watershed that has an area of 10 acres, or I've also said how many square meters that is to save you the conversion step, for a storm intensity of 4 inches per hour, or its corresponding SI units, and then the runoff coefficient of C equals 0.7. Anybody want to refresh our memory? What is a runoff coefficient? What does that 0.7 represent? Okay, yeah, great. That's a wonderful way to think of it, is that of the water that's coming out of the sky, 70% is running off. Now, that means this is at a very special condition, though. The rational method is for peak flow. And so it's not at the beginning of the storm that 70% is running off. You know, those first few raindrops, maybe none of those are going to be running off because the surface has to become wetted down. And so we'll talk a lot about these initial abstractions that have to be satisfied before the peak. But this Q that we have in the formula there, maybe it would be even more accurate if we said Q sub and then subscript here, peak. So the peak runoff during some storm will be this coefficient, which is the fraction of runoff to total precipitation, I, the intensity of the rainfall, and then the area. All right, so let me pause this recording, give you a few moments to calculate the Q peak in traditional units and also in SI. All right, so on this example, the main thing I want to illustrate is that in the traditional units, you can take the time to convert inches per hour into feet per second, and that's the intensity. You can convert the area from acres into square feet, and then you, in this case, I think 28.2 cubic feet per second is what you're supposed to get if you do all of the units conversion. But coincidentally, just because of the relationship between acres and square feet and inches per hour and feet per second, if you don't bother making those conversions, you can leave the intensity in inches per hour and you can leave the area as acres, and you'll get approximately the same flow rate. So instead of 28.2 cubic feet per second, you'd get 28. I think in very rare cases, someone might multiply this by 1.008 as some units conversion factor, but we don't usually bother with that units conversion factor because the C value is estimated anyhow, and it's really an imprecise thing to judge what is the runoff coefficient. That's not something that is very rigorous or quantitative. It's usually just more of a rule of thumb estimate, and there are tables in the textbook that can help you with that. But any questions about that rational method review of the units? What did the SI units work out to for the flow rate? Q is what in terms of cubic meters per hour? Anybody get that? 2,878 cubic meters per hour. Okay. Rational method. So this is the one thing that if you walk away from the course not understanding the rational method, that's really a problem. It's very useful and obviously very simple. Okay, so what we're going to be talking about over the course of today and next class period is how to prevent flooding in urban areas. Now, urbanization presents some real challenges when it comes to hydrology because inevitably, when people move into an area, they make the surface kind of impervious to infiltration from precipitation. And if you think about the area around this campus, what did people do to previously what was here compared to what's here now? So in the past, there would have been vegetative cover over the soil, undisturbed soil. But when we do things like take soil grading machinery over the soil, or even just walking on it, you reduce the ability of water to infiltrate into the soil, and then that really reduces the infiltration when you put pavement down over the surface or create a roofed building over an area. So in general, the land becomes kind of impervious to infiltration, and so a greater fraction of the rainwater is going to be running off, and that exacerbates problems of flooding. So there are some photos here of flooding in some third world countries, and part of the reason for more frequent flooding in those places as compared to more developed urban areas is that we have the luxury of stormwater drainage systems. Huntington's stormwater drainage system isn't the best, but it's better than the stormwater drainage system in Manila, Philippines, for instance, which is where a lot of these photos were taken. And so flooding is a real problem. Japan has it's also in Asia, like these photos were taken, and they get a lot of rainfall in parts of Japan that could cause havoc. And so they took a very aggressive, hands-on approach to avoiding flooding. And let's watch this video about the approach in Japan. Okay, it gives me time to figure out how to work the speaker.
Below these fields, on the outskirts of Tokyo, through a door behind a government building, sits a remarkable feat of engineering, an elaborate complex and a massive tunnel aimed at preventing widespread flooding in this low-lying area. Takashi Komiyama explains to us how the system works. A tunnel running more than 6 kilometers for nearly 4 miles connects 5 underground shafts that collect water from above. And how big are these shafts or tanks? They're about 70 meters or about 230 feet deep. To put that into perspective, that's big enough to fit a space shuttle or the body of the Statue of Liberty. At the heart of the system are these 4 turbines powered by jet engines, similar to those used on a Boeing 737. When set in motion, they can drain the equivalent of a 25-meter swimming pool in 1 second, able to funnel water from the tunnel and tanks to a nearby river. The system cost roughly $3 billion to construct, and it's been used nearly 70 times over the past 10 years. As you can see, the size of this complex is simply staggering. It is something that few major cities could ever really accommodate underground. The room I'm standing in right now is bigger than a soccer pitch and more than 5 stories high. And when we asked Takashi about the flooding in the United States, he recognizes this system is built to cope with heavy rains, not a storm surge off the ocean. Still, the idea could help engineers think about what may be possible when it comes to trying to contain Mother Nature. Alex Holbert, CNN, Saitama Prefecture, Japan.
All right. So, I mean, that's pretty remarkable. Anybody remember how much money they spent on that? $3 billion, right. Later in the semester, towards the very end, what we're going to do is look at some engineering economy analysis of flood control measures and trying to get a grasp on when spending is justified versus it's not. You know, the long-term costs of flooding and how different types of flood control measures can prevent flooding or reduce the risk of flooding, because even that system with its jet engine powered pumps and soccer pitch size area, even that system will be overwhelmed and will fail occasionally. You know, it's just all a matter of probabilities. There's some very low probability, high intensity storm out there that could cause that system to fail and flooding to occur in spite of it. But if you look at the damage or the reduced risk of damage, sometimes $3 billion is a small investment to reduce the kind of damage that can occur. Okay, so in most cases, the way that the stormwater is accommodated is by gravity flow. And though that underground vault, what it used those big pumps for was to lift the water from the underground vault and deposit it into a nearby stream. More commonly, they will have a stormwater drainage network that discharges directly to a stream, or maybe after just very rudimentary cleaning, like settling out grit and skimming the oil off of the top of a settling pond. But to illustrate how StormCAD works to model these open channel flow type situations, we're going to work through an example like pictured on the screen there. And it's a little bit different compared to water gems, because remember, in water gems, what you were doing is you were trying to balance the pipe diameter with pressure at a single junction. But in these cases, most of the time, before the system fails, it will be open channel flow. You can get something called surcharge in a storm sewer, where the water is all the way to the top of the pipe and actually is a little bit pressurized. But when you have surcharge, that's when you've got water coming out of the manholes. We looked at a video of a manhole cover blowing off, right? Like exploding and landing on a car. So that's what happens when a stormwater drainage network becomes pressurized, and it's considered not a great thing. So how many of you, I'm just curious, how many of you have installed StormCAD on your computer since I sent that last minute All right, so some of you have. That's great. If you haven't, that's okay. I don't think you're going to be at a disadvantage. There are a number of things I want to show you how to do today, and if you're not doing them now as we go through it, then you can certainly do it on your own, or just keep this video off to the side as you work through the homework assignment, because the homework assignment is the same drainage network as we're going to look at for the example. For the example, though, it's just the upstream part of the network. It's this 3.1 and upstream of that, whereas I'm asking you to design the entire network for the homework assignment from a variety of sizes. Okay, so let's see if they've got StormCAD on here, and if not, I'll have to remote connect to my office computer. Nope. All right. All right, so StormCAD, here we go. Here it is. Create a new model. We're just going to start from scratch here. And we're not going to bother importing the map in the background. We could have a map in the background similar to what you did in the project for hydraulic engineering last semester when you had the city image and you were drawing the pipes in the back. You could do that for this, but you don't have to, because in the example we've got the known areas of each of these basins. Let's see. Let me bring up the assignment just so we can look at the image on the screen. Okay. Okay, so in the example, what we're going to do is we're going to find out how much water is making it into each of these inlets, and then trying to figure out how big the pipe should be to accommodate the water that's coming in during the peak flow. So remember what we were saying earlier about the rational method is that the Q you get from Q equals CIA is the peak flow rate. And we want the system to be sized to accommodate the maximum flow from a certain return period storm. There is an intensity, duration, frequency curve on the handout that I've just given you for the homework assignment. This curve, what it is showing is for a certain storm duration, how intense the rainfall could be expected to be. We'll go into a lot of detail about rainfall later in the semester, but the way to interpret this is that a storm that has a continuous duration of 30 minutes maybe could only achieve an intensity during those 30 minutes of 2.3 inches per hour. But in the case of a shorter duration storm, like a storm that's only 5 minutes in duration, the intensity is going to be a lot higher. And you've probably observed that before, that if you look out the window, when my office was over in the old engineering building, I'd love it when it would rain, because you could hear it on the roof and had a great view out the big windows there. And people would just sort of stop and look at the rain, and also look at people stumbling into puddles, which was always great. But for a short duration, there would be a really high intensity. But part of the reason why it can't maintain a super high duration, super high intensity for a long time is that the clouds are moving. And you can have a concurrence of lots of clouds over a high elevation, a big depth of cloud coverage only momentarily. But it would be more common to have the depth of the atmosphere that's currently is experiencing precipitation to be narrower, and so more spread out. And that's part of the reason why intensities are low for longer durations. So in the case of this map, how do you think we know what duration to use? Let's say in the case of this 2.2, that's just a nomenclature for, it's an inlet that we're calling 2.2. Should we use a 5-minute storm duration for the water getting into there? Should we use a 30-minute storm duration? Any ideas on how it works with which duration to use?
You use the time of concentration as a duration.
Okay, so the time of concentration, remind us what that means.
So however long it takes from the most hydraulically busy portion of the watershed to the power.
Very good. That's exactly right. So if you have a really big contributing area, it's going to take longer for the water to flow from all points of that big area until it gets to this inlet. If you have a small contributing area, then it doesn't take long for the water to travel to get to that junction. So in the case of 3.2, you can see this is a relatively small area. So the water travels from these far corners towards the inlet in probably less time than it would take for 1.2. If you look at where is the delineated area for 1.2, this, I know it's a little hard to read because we've got both the contour lines and the streets and then the watershed contributing areas. But the contributing area for 1.2 is this line, and it's a big area. And so it's going to take a long time for all of the water to finally travel to that inlet. And so the time of concentration would be longer for catchment 1.2. So here we have a table of times of concentration. So 1.2 has a time of concentration of 9.2 minutes. But if we look here at 3.2, the time of concentration is 5.9 minutes. So less travel time. And so we would use the time of concentration on this intensity, duration, frequency curve. We'd use that as the governing duration and find the rainfall intensity from that. Okay, so Q equals CIA. In the background, the computer is going to be doing all these Q equals CIA calculations and then also doing travel time calculations, because it takes a certain amount of time for the water, once it gets into the inlet, to travel through a pipe. How do you think it's going to be doing that? What are the variables it's going to need to calculate or estimate the travel time through the pipe? Okay, the length of the pipe, exactly, good. What else? How does it, okay, velocity. How is it going to estimate the velocity, the travel velocity through the pipe? Good. Slope, yeah. Yeah, so it's actually going to use Manning's equation to calculate the relationship between flow rate and the pipe characteristics. And so the slope, the material type, the diameter. And so we can solve Manning's equation for Q, or if we know the diameter of the pipe, we can solve Manning's equation for velocity. And so it's going to know the length of the pipe, which we'll have to put into the system. And then in the background, it's solving both the rational method and Manning's equation to calculate flow rates and travel times. And then it combines it all together. And so it's got all these delays that it's accounting for, and it wants to know when does the water arrive in a certain pipe from different locations. And so here at junction 2.1, the water's actually coming from 3 locations as it enters pipe C. You know, the water's coming from pipe A, which had an upstream inlet. The water's coming from pipe B, which has this upstream inlet. But then there's also, here at this manhole 2.1, not only is that a junction of 2 pipes coming in, but more surface water is also going in at that inlet. So it's accounting for all these things simultaneously. All right, so here is StormCAD, and we are going to begin by just drawing some elements. And let's see what version I've got here, because I would imagine that probably the version that you have may be a little bit different. Let's see if I can get the about here. Where do they do the, maybe in help about. All right, what version, for those of you who have it installed, what version are you using? Does it say, okay, here it is. I'm using 10.000.4. Is it still version 10 that you've installed? 4.5. All right, so I'm guessing they've made some very minor bug improvements, but hopefully the ribbon looks the same and the button location is the same and so on. Okay, so you use this layout button to begin drawing, And if you right-click, then you can change what you're going to be setting down. And in our case, if we're going to be working through an example, let me give you the example. Boy, that punched it in an odd place. The printer punched it at the top instead of the sides. So I'm going to have to look into that. This is the example we're going to work through. We're going to just sort of analyze how the network is doing. All right, so we want to create kind of like a skeleton structure of the network on StormCAD for this network that's shown here. So we've got 1, 2, 3 pipes. Pipe A, Pipe B, and Pipe C. Let me bring up the example. Folder. So here is the network that I want to schematically build a representation of in StormCAD. And so the things that I have to put into the network, I have to put the pipes, the inlets, an outlet, and then watershed areas. Okay. Now, think about what I told you it's solving is the rational method and also Manning's equation. And so you know both of those formulas, and you know what the variables are that go into there. So we have to define all of the characteristics that will satisfy the unknowns in those equations. And so, for instance, for the watershed areas, it's not just the areas, but it's also the watershed characteristics, like the C value. Okay. For the pipes, we have to tell it the roughness, the diameter. What else does it need to know about for the pipes? The length and slope. Very good. On the subject of length and slope, let me show you something that illustrates how to specify the slope of a pipe in StormCAD. So this is a side view of the ground surface. And here's the ground. And then here are a couple of manholes connecting a pipe. So there's a pipe. And in this case, the pipe matches up with the bottom of the manhole in upstream, but in the downstream it doesn't. And that happens sometimes, that they'll have a pipe come in at a different elevation, and then that gives you some capacity for trash to accumulate in the manhole, and then you can vacuum it out occasionally through maintenance. Okay, so what we're going to have to identify is the ground elevation, which can be fully independent. The slope doesn't have to be the same for the ground and for the pipe. So we'll identify the invert elevation of the catch basins, the diameter of the pipe, and then the crown elevations for the pipe. And so here you can see, since this is a 1 foot diameter pipe, if it matches the invert of the catch basin at 96 feet, then the crown elevation is 97, meaning the inside top of the pipe, not the outer diameter of the pipe. So if this is a 12-inch diameter pipe, we're talking about its actual flow capacity diameter and not the outside diameter. Because if this is a concrete pipe, it would probably have a thickness of maybe approaching 2 inches. And so its outside diameter would maybe be 16 inches, but its flow diameter would be 12. So here, the crown elevation downstream doesn't match the invert elevation. And so there can be some independence there between them. Okay, now back to working with StormCAD. So the inlets, we're going to have to give it the elevation. The outlet, the elevation. The watershed areas, the C value, and then the corresponding storm information, the storm data. This curve is going to have to be input into StormCAD so that it can look up what intensity to use for a certain time of concentration. All right, so let's do it. We're going to right-click here to change the option that's going to be dropped down. And I'm going to choose a catch basin. And this rectangular symbol identifies something coming in. So for me, this is going to be here 1.1. Now, it's not called 1.1 yet. It has a default naming system of its own. And I don't have to click in a certain point because I'm going to do user-defined lengths, similar to what we did in WaterCAD when we wanted to just override what it estimates the length is. Oh, I guess one thing we ought to do is make sure that the units are going to be right. I see down here that it's feet, and this example is in traditional units, and so I don't need to change into SI. The traditional units will be fine for this example. Okay, so catch basin 1. This is 2.1 that I'm dropping down. Now I'm going to right-click and make 3.1 is just going to be a catchment as well. And then right-click and make an outfall, and that's where the water goes into a river. And then I press escape to finish that. Now I'm going to do one more catch basin off to the side, which is connecting into 2.1. Now, the order that you click things provides it with an assumed direction. So the first click is upstream, the second click is downstream, is what it assumes. And you can reverse that assumption if needed. But just so that this matches the image file that I'm working with, I'm now going to change the names of these elements. So I'm going to rename the annotations by going into the table. And the flex tables are the same that you remember from water gems. You can just click on an element and change its properties one thing at a time. You know, I could change that from CB1 to 1.1, and then it will update its name. Or I could open up the flex table for the catch basins, and then I could change the rest of them all at once as a batch. And so right now what it's calling catch basin 2, I actually want that to be called 2.1. This catch basin 3 is the one I want to be called 3.1. Catch basin 4 is 1.2, according to that example that I handed out. And since I'm in it already, since I'm in the catch basin table, I might as well put in some of these ground elevation data that I've got. In the data that's provided, we've got the invert elevation of the junctions, and then we've got the data for the pipe, but nothing about the ground elevation. And so let's make an assumption here that the ground elevation is always going to be 10 feet above the invert elevations that are listed. So in the junction table here, oh, that's not the example. Here's the example. All right, so these inverts are the bottom of the catch basin. And since we don't have, oh, actually, we could use this contour map for the ground elevations. Okay, so we can estimate the ground elevations from the contour map. We don't have to just like make an assumed elevation above it. So for 1.1, for instance, it's between 730 and 735. It looks like 1.1, the ground elevation is about 733. Okay, so the ground elevation for 1.1, 733. For 2.1, it looks like that contour there is the 725 contour line. That is this contour line. The ground elevations aren't the most important piece of data that we'll be putting in today, and so that's why I'm sort of not too worried about being a little bit just on the estimating side of things. 727. For 3.1, probably 723, and 1.2, maybe the ground elevation there is 727 also. All right, but what is important is the invert elevations and the lengths. And so I do have the invert elevations in more exact terms here. So from the table, it tells us that 1.1 is 730.5, 2.1, 722.7, 3.1, 718.36, 1.2, 723.45. So we're putting in the invert elevations. Now, why is the length yellow here? The yellow means we can't, man, it's really dark out there. It's like 8 p.m. dark. It's going to rain. After class, you guys should go get rained on in the parking lot so you can finish your homework. Okay, anybody remember from last semester working with water gems what the yellow meant? Right, it means you can't type in these yellow fields, and so we have to go over here and see if user-defined length is an option. And if it's not, we can open up the table and make it an option. Where is that? Like the list of, there it is. All right, so has user-defined length, I think, is what we're looking for. Maybe user-defined length. Oh boy, they changed the terminology. So we'll go through this entire list to try and find where the user-defined length is. If you see it, call out. It might just be under length, I suppose. Oh, you know what? I know what the issue is. We're in the catch basin table right now. It will be in the conduit data, right? Yeah, we're getting off track. Okay, so we need to give it the elevations, and I think that's all that we need to specify so far, except for the inlet location here, change it to in sag for all of them. And the reason why is that switching it to in sag forces it to assume that 100% of the water that flows over that inlet is going to be captured by the inlet. And one of the capabilities that WaterGems has is to kind of estimate what fraction of the water that flows over a grate is actually going to be captured by it. And that's kind of beyond the scope. That's like an additional level of sophistication and complexity that I don't want to introduce for this example. So just change the inlet location to in sag, and if you don't, you get an error message in some cases that you'd have to eventually go through and debug and resolve. All right, so we put some information in for the inlets. Now let's go back to the table for the lengths and see if we can find the has user-defined length in the flex table for the conduit. Okay, here it is, has user-defined length. So we can turn that on and then put in the known lengths for each one of the pipes. And so pipe 1.1 to 2.1, that is conduit A. I guess we can change these names to the correct conduit naming that's similar to the image. So 1.1 to 2.1 was conduit A. Okay, conduit 2 is the one that we called C. Conduit 3 is not on this, so we're going to call that drain, because that's the one that goes to our outlet. And then conduit 4 was pipe B. Okay, so we have all of our pipe names, and we're going to have to put an invert elevation in for that outlet, because right now it's assuming it's at 0, and that would be an awfully steep pipe if it's at 0 and everything is up in the 700s. But yeah, it's like a water, a really crazy water slide or something. Put in the user-defined lengths that comes from the pipe table here. We'll use these lengths for the pipes. Okay, so pipe A has a length of 390. Pipe C, 177. The drain pipe, we just have to make something up, because that's a pipe that has to exist in the network for it to be modeled. But what we're sizing, we're doing this whole example to figure out how big pipe A, B, and C should be. And we just assume that downstream of this last junction is just something that's going to be able to accept the flow that we give it. And so we want to make this last drain pipe really big and really steep so that it's not the limiting factor. So it's kind of outside the scope. And so I'm going to say that its length, it doesn't really matter. I'll say 50 feet. Okay, and then pipe D. What's this last pipe here? Oh, B. I'll learn my alphabet eventually. Pipe B, okay, 183 feet. All right, so we got all the lengths in there, and circular pipe, the diameters. We don't know how big the pipe needs to be yet, so we'll just start with 12-inch. This Manning's N corresponds to a concrete roughness. All right, so we've defined basically everything we need so far. What's interesting is you'll see it's already doing Manning's equation. It's solving, if the pipe was full, what would the capacity be for that pipe? But what it hasn't calculated yet is the ratio of the actual flow rate during peak conditions to the capacity. This percentage is going to be a really useful way for us to know if the pipe is oversized or undersized. So far, it's not defined because it hasn't actually calculated the rational method. It has calculated Manning's equation already, and that's the result of this. So you'll see that this drain pipe has a super big capacity because, remember, its elevation is down at 0. So that's fine. It's not going to cause any calculation errors for it to have such a big capacity. Now, pipe B, that's a little bit strange. Why is its capacity set to 0 right now? I'm wondering if maybe for pipe B I haven't defined something the right way yet. So let's look at the inverts. For pipe B, upstream and downstream. 1.2, it connects 1.2 and 2.1. So there should be some slope to it. Let's go back to the junction table and make sure that I type the elevations in right for the inlets. Okay, so we want to check 1.2 and 2.1. So 1.2, the invert elevation, 723.45, and 2.1, 722.70. That's so strange that the capacity it's calculating for Manning's equation, so it does have slope, so it's not the slope. Its slope is really low, I guess. Is the issue there is okay, so it's calculating capacity now. It was saying 0 before. All right. So what are we missing here? Think about like a schematic representation. What haven't we told the simulator? Watershed areas, right. We haven't told it the watershed areas or the storm data yet. So we need to draw a watershed area. And the way that you do that is right click. I'm drawing a blank here. I know there's a way to do it. Where is it? No, it's none of those. Catch basin. Catchment. All right. This is just the symbology for it. Man, this is... okay, catchment. All right, so layout. Just draw some area. I'm going to pause this recording because this is not useful. Well done. All right. So here's what we're going to do. Let me select this catchment I just drew and delete it. All right, so on the Layout tab, Catchment, you start to draw it, and it doesn't have to be to scale, because just like we can do user-defined length for the pipes, we can have user-defined catchment areas. We just have to create some sort of a symbolic representation for the area that goes into each one of these junctions. And it actually, the area doesn't have to be drawn on top of the junction. And just to illustrate that, I'm going to right-click, right-click, right-click. It can be whatever shape, and then your last one should be, no, those were all left clicks. The last one should be a right-click where you can do done. Okay, so there's a catchment. Here's one. Done. Here's going to be one. And then another one. All right, so we've got now 4 basins, 4 catchments, and if you look at the table that's provided on the example here, we have the characteristics of each one of these catchments. And so we need to tell it the name, the area, the C value. So let me go over here to the table, the flex table for the catchments, and then we can rename them to match what is in the example. I think it's raining out there. All right, so catchment 2 is the one that we're going to call catchment 1.1 because it has the same name as the inlet that it goes to. So catchment 3, we're going to call that catchment 1.2 because that's the area draining into catch basin 1.2. So catchment 4 is actually 2.1. Catchment 5 is 3.1. All right. Now, this outflow element is really important because it doesn't know yet what area dumps into which catch basin. You'd think maybe it would just sort of estimate based on the physical proximity, but it doesn't make that assumption. Rather, what you have to do is you have to make an assignment. And so I'm going to assign for why do I have this catchment 5? Okay, so it's not until I move out of the field that it reassigned the name there. Okay, so for 1.1, if you click on the little ellipsis, this dot, 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 then it's going to allow me to click the catch basin that it should be assigned to. And once I do that, it drew this little dashed line, and that little dashed line tells it all of the flow from that area is assigned to that inlet. Okay, so now I can do the same thing for 1.2. I'm going to click on that outflow element field. It brings up the ellipsis, click on the ellipsis, and now it's saying where should 2.1 be assigned. I could assign it in the wrong spot. Oh, wait, which one was I assigning? Yeah, 2.1. I don't know why this is in red. Okay, so 2.1 is going in here, and then you see the dotted line just to confirm that it's all going in the right spot. 3.1 goes to there. All right, so we've assigned where it goes, and now the areas we can put into the table from the data that's given. And the C values for each of those watersheds. So 0.65 for the first, 0.8 for the next, and so on. All right. Time of concentration, that's what you could estimate by going to a place and watching the water travel from all points in the watershed, or you could use one of the estimating schemes, curve pitch or all the other methods. So right now it's in hours. I want to change it since I have mine times of concentrations defined as minutes. If you right click up at the top of that table, then it'll allow you to change the units from hours into minutes. Okay, so what I did was I right-clicked on the column, units and formatting, and it previously was in hours, and I changed it over to minutes. And I guess I could change the precision display as well. Okay, so that first one is going to be 11 minutes. Then 1.2 was 9.2 minutes. 2.1, 13.7 minutes. Finally, 8.7 minutes. All right, so I've defined everything that I need to for the times of concentration. Let me zoom out a little bit, make sure that we've... Last thing I have to do is I have to give it the storm data. And I'm going to create a, here in storm data, a user-defined storm event. So here under user-defined, I'm going to do a new user-defined. Okay. And I'm going to put in the same information that's in this table. So times of concentrations and intensities. So I want it to have that curve. So I'm going to add a return period. This is, let's assume, maybe a 5-year storm. Okay. And then I'm going to do, no, not a range, duration. Okay, so we're going to have a duration of 5 minutes, another duration of 10, 15, 30, and 60. Okay. And then the intensities that correspond to each of those durations, 5.4 inches per hour, 4.2, 3.2, 2.3, and 1.4. Okay, so we've got a curve here that's approximately similar to what we had. You'll notice here that it's a linear scale on the x-axis, whereas the figure that I gave you, it was a logarithmic scale. So that's why its shape is a little bit different from on the handout. But now we have that storm that's defined. We can close that. And oh, we're running low on time here. It's 10:45. Just really quickly, I want to show you how to actually run this. We'll continue with this example in class on Thursday. So definitely, I guess the first thing we should have done was saved our work. I'm going to do that right here. Save and StormCAD 2017. So if you're with me so far, or regardless where you're at, save that example. What we're going to come to next time is telling the program to run the simulation and then find out what's the flow rate in each of those pipes compared to its capacity. All right. So before we finish, let's just review back over these announcements. All right. The homework assignment number 2 is due on Thursday. I've got office hours today, tomorrow, and I'd be happy to respond by email if you've got questions on that assignment. But when we get together on Thursday, we'll start with the quiz, then we'll continue this example, and then we'll talk a little bit more about stormwater pond sizing. All right, so that's it for today. I'll see you on Thursday.